Here's our pending problem from last week. I missed Friday, so we'll just go over this today. We had a car driving towards a point and a camera focused on the car. As the car drives to the point, the car is approaching the point at 100 feet per second. And I cared about two different rates that were related to that. The distance between the car and the camera, that angled distance between the car and the camera, and how fast the camera is rotating. So how fast is the distance between the car and the camera changing at various points? And then how fast is the camera rotating at various points? All right. So what is missing from this problem is some labels on things. So I'm going to give this distance x, the distance from the car to the point, the label x. I think I call that point C, so everything would be labeled with C. I don't know why I did such a mean thing, but I did. So x can be the distance from the car to the point, and now we can give a name to that 100 feet per second. That's how dx is. That's how x is changing with respect to time. So what that means is that we can call dx dt. So with this information, we can say that dx dt, the rate of change of x with respect to time, is 100 feet per second. But since the car is getting closer to the point, we'll call that negative 100 feet per second. And for convenience, let's just measure x in feet. So the reason that we want to make this negative is that the distance between the car and the point is decreasing. In 1 second, when the car is 100 feet from the point, 1 second later, the car will be 0 feet from the point. So the derivative should be negative. So if I give the distance from the car to the camera, that value is also changing. The only thing fixed here is the 60 feet. So I'm going to give the distance from the car to camera a different name. So I'll call that R. And that is also going to be in feet. So one of the rates that we're looking for is dr dt. So dr dt will be the rate of change of the distance from the car to the camera with respect to time. That is one of the things that we were looking for. How fast is the car approaching the camera as a function of time? So these rates are related. I need to find a relationship between the variables, and we're going to use the Pythagorean theorem. That's because we have this gigantic right triangle. So x squared plus 60 squared is equal to r squared. R is the hypotenuse in this case. So x squared plus 60 squared is r squared. Here's a relationship between r and x. Now we have a few things that we can do. We can write r as a function of x, take the derivative that way, or we could use implicit differentiation. In either case, when we take the derivative, we'll be taking the derivative with respect to, or if we solve for r and then find the derivative, we'll be finding the derivative of r with respect to x, and we'll have to multiply by dx dt. So if I solve for r, if I use that strategy, the thing that we want to notice is that we'll get a function of x, which is not what we're looking for. We're not looking for dr dx, we're looking for dr dt. So we would have to use the chain rule. Our other strategy is to use implicit differentiation. Both strategies perfectly valid. At time of filming, I'm probably leaning towards implicit differentiation since that's the thing that we worked on last week. So I'm like, well, here's implicit differentiation. But as far as like doing this problem, you can be like, oh, nah, bro, I'm not doing that. Solve for r. So if we solve for r, here's what that would look like. R would be the square roots of x squared plus 60 squared. 6 squared is 36. 10 squared is 100. I'm going to use a modern radical and say it's to the 1/2 power. So when we use our derivative rules, if we find r prime, that'll be 1/2 x squared plus 3600 to the negative 1/2 times the derivative of the inside, which is 2x. The 2 and the half will cancel out, and I'll have x over the square root of x squared plus 3600. This is the derivative of r with respect to x. But we're not interested in the derivative of r with respect to x. We're interested in the derivative of r with respect to t. So if I want the derivative of r with respect to t, the chain rule says multiply dr dx by dx dt. Any questions? So what would this look like using implicit differentiation? Oh, so at this point, if we want dr dt at various values of x, we can just plug in the value of x here, calculate what the value of r is down here, and the dx dt is our constant negative 100 feet per second. If we're going to use implicit differentiation, this has to come out the same. We're going to take the derivative with respect to t all the way through. The derivative of x squared with respect to t, I'll write 2x. That's the derivative with respect to x. Then I have to multiply by the derivative of x with respect to t. The derivative of 3600 is 0, so that's no problem. The derivative of r squared is 2r with respect to r, and then I have to multiply by dr dt. The important things that we want to recognize here is that we can't just say the derivative anymore. We have to know the derivative with respect to what variable. And in this case, we have to know that we're doing implicit differentiation because r and x are related to each other. From here, we can solve for dr dt. It's being multiplied by the 2r, and so I'll just divide both sides by 2r. The 2's cancel out. I end up with x over r times dx dt. And we notice that this is the same thing we got when we explicitly solved r as a function of x. R is equal to the square root of x squared plus 3600. So we can see how they're related. Those are the same if we combine that with r is the fact that r is the square root of x squared plus 3600. We notice that x and r are both positive, so this is going to be positive with dx dt being at negative 100 feet per second. That's going to give us a dr dt of that's negative, and that makes sense in the context of the problem because the distance between the car and the camera is also shrinking as the car approaches point C. Any questions? Is everybody okay? Everybody looks stoked. I'll just put this problem on the final and we will crush it. The other question was about how fast the camera is rotating. So in this case, all we really need is this part. We got that fixed 60 that we want to use, and then I've got x and dx dt. Here the question is about what is d theta dt. So I need a relationship between theta and x. We can use r if we want, but because we have that data, so I could say 60 is adjacent to theta and r is the hypotenuse, or I could just use x as the opposite. So I could set up my relationship as tangent of theta is opposite over adjacent. This doesn't have any units because x is in feet and 60 is in feet. So tangent of theta is just a ratio. The things that we want to watch out for here is that tangent is not an invertible function. It's probably an invertible function since theta is going to be less than 90 and at most negative 90. So we're probably okay with inverting tangent. So we should note that tangent is not generally invertible. If I tell you the tangent of theta is something, unless there are other specific conditions that tell you that tangent will be between negative pi over 2 and pi over 2, we can't just tangent inverse both sides. Just like if I said x squared is equal to some number, you can't just square root both sides. X squared is not invertible. So tangent is not generally invertible, but since theta will be between negative pi over 2 and pi over 2, theta will be between negative pi over 2 and pi over 2. If theta is equal to pi over 2, that means that the car is infinitely far away and we're not looking at it anyway. So we have both of our strategies. We could solve for theta as a function of x, or we could just do implicit differentiation. We still have our two strategies available to us. If we solve for theta using arctangent, which we've decided is okay because theta is going to be between negative 90 and 90. When theta is equal to 90, it's strictly less than pi over 2, so strictly less than 90 because that would mean that there's two 90-degree angles in this triangle and that won't fit. We can't have a 0-degree angle up here, not in Euclidean space. We do have to remember the derivative of arctangent. So the derivative of theta, a derivative of arctangent is 1 over 1 plus x squared times the derivative of the inside, which is 1/60th. Now, this is the derivative with respect to x but we were looking for the derivative of theta with respect to t. So that means we'll have to multiply by the derivative of x with respect to t using the chain rule. We also might look at this and say, algebraically, this is aesthetically not very nice. So if we square this all out here, this is going to be 1 plus x squared over 3600. I'm going to multiply everything by 3600. So that's going to be 3600 plus x squared all over 3600. If I get a common denominator, and it's a 1 over. So if I flip this over, I can write this as 3600 over x squared plus 3600. And then I can cancel one of these. All this is being multiplied, divided by 60. 3600 divided by 60 is going to leave us a 60. So maybe we clean this up a little bit. So I did a little algebraic sleight of hand there. So I roll my sleeves up, nothing up my sleeves, algebraic sleight of hand. So now for various values of x, we can plug in the different values of x that you were given here, and then multiply the 60 over that by the dx dt. Good question. How's everybody okay? Everybody looks all stoked. We look like this. Because we're 3 weeks away from the final. Feel like all super stoked. Like, oh, we're almost done. I'll put on a happy face. So the other strategy that we have is implicit differentiation. So for that, we would need to know, instead of the derivative of arctangent, we would need to know the derivative of tangent. Derivative of tangent is secant squared. But that's the derivative with respect to theta. I would have to multiply by the derivative of theta with respect to t. The derivative of x over 60 is 1 over 60, but that's the derivative with respect to x. I would have to multiply by the derivative of x with respect to t. D theta dt is what we're looking for. Dx dt is the rate that we have. So what we're solving for in this case is not theta. We're solving for d theta dt. So we'll divide by secant squared, so we'll multiply by cosine squared. And at first, this looks radically different than what we had before, but it's not radically different. Theta's and radians, it's radially different. If we go back to our original triangle, If we go back to the original triangle, the cosine of theta will be adjacent over the hypotenuse. So if we go back to that cosine of theta, adjacent is the 60, and the hypotenuse is this r. And we had previously calculated r to be square root of x squared plus 3600. If we then take that 60 over the square root of x squared plus 3600 and then square it, we get 3600 over x squared plus 3600. And if we divide that by 60 for this 60 over here, we see that the expressions that we have are the same in both. So in this case, we don't even have to calculate what theta is. We can figure out how fast theta is changing because you were given different values of x. So we can calculate what theta is using arctangent, but we don't have to calculate what theta is equal to. We only care about what the cosine of theta is equal to. Any questions? That's everybody okay? All right, so this problem involved related rates. We had two quantities that were changing. Those quantities were related by some equation. So their rates, the derivatives were related by, were also related. In both cases, we had a few different strategies that we could employ. Write an explicit function, we still had to use the chain rule or use implicit differentiation, which is our new technology. One thing I should note up here is that in the second half of the problem, we were concerned that where tangent was invertible. And since theta was only going to be between negative 90 and 90, it was okay to invert. In this case, when we write r as the square root of x squared plus 3600, we do have to note that we're taking the square root, which is r squared is not an invertible function. But in this case, our choice is plus or minus the square root, and we want the positive square root because r is going to always be positive since it's a distance. So r squared is equal to some constant, tells us that r is equal to plus or minus the square root of that constant, and we want plus. All right, so that's going to do it for this problem. I know we didn't actually calculate these values, so we can plug in and check our values into both, make sure that they are the same. That's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing. And in case you missed it, we are 3 weeks off of the final exam. Monday, May 20th from 8 to 10:40. That's it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.